Hi everyone, I am Garvit Dewan, an undergraduate student in computer science at the Indian Institute of Technology, Roorkee, India. So today I'm going to present on distributed data structure for the partition global address space model. I was working on this project under Google Summer of Code with CHIUW with my co-author Louis Jenkins as my mentor. Louis is currently pursuing his PhD at the University of Rochester. So the goal of this project was to enable the development of non-blocking algorithms and data structures in the CHIUW programming language, both in the shared memory and distributed context. But however, the concepts that we have adapted don't really limit it to just CHIUW. They can be adopted in pretty much any other programming language. So let's begin. Let's discuss some background first. While reading about this project, one might wonder why we need non-blocking algorithms in data structures in the first place. Well, there are several disadvantages of using locks, mutexes, semaphores, spinlocks, etc. in algorithms. First and foremost, using locks makes the algorithm prone to several problems such as deadlocks, live locks, priority inversions, etc. These problems can be difficult to prevent and may halt the progress of threads. In terms of granularity, locks can either be coarse-grained and fine-grained. While coarse-grained locks may seem to be a good solution to avoid deadlocks, they generally involve higher lock contention. This results in lower scalability. Fine-grained locks seem to be the solution to the contention problem and do result in increased scalability. However, fine-grained locks may involve several lock dependencies, which increase the chances of deadlock or live lock. Non-blocking algorithms prove to be advantageous against blocking algorithms. How we may? Non-blocking algorithms have a property of liveness, which is the property of progress of threads in a system. It is of three types, in the order of increasing guarantee of the progress: obstruction-free, that is, threads finish in finite number of steps if not obstructed. Obstruction freedom is the weakest natural non-blocking progress guarantee. An algorithm is obstruction-free if, at any point, a single thread executing in isolation, that is, with all obstructing threads suspended for a bounded number of steps, will complete its operation. Lock-free, at least one thread finishes in a bounded number of steps. Lock freedom allows individual threads to staff but guarantees system-wide throughput. An algorithm is lock-free if, when the program threads are run for a sufficiently long time, at least one of the threads makes progress. For some sensible definition of progress, of course, all lock-free algorithms are obstruction-free. Wait-free. All threads finish in a bounded number of steps. Wait freedom is the strongest non-blocking guarantee of progress, combining guaranteed system-wide throughput with starvation freedom. An algorithm is wait-free if every operation has a bound on the number of steps the algorithm will take before the operation completes. All wait-free algorithms are lock-free. Non-blocking algorithms provide scalability while also guaranteeing liveness. However, non-blocking algorithms are generally quite challenging to create. So, the problem with non-blocking algorithms and data structures is not simply their creation. Memory reclamation is another big challenge. Specifically, let's talk about each of the possible reclamation of object we reclaim by other threads. If an object is reclaimed too early, that is, it is reclaimed by other threads might access it later, it may lead to the case of use after free. As a result, this may lead to undefined behavior. Never reclaiming any object leads to memory leaks and may exhaust memory. Not all programming languages and systems have a built-in garbage collection system. This includes SAPL programming language as well, and several other languages, for example C, C++. These problems need to be addressed. The former needs to be addressed for validity of the program, while the second one is necessary to ensure that programs can run without unnecessarily exhausting resources, memory in particular. Another issue is that if conventional log-based concurrent garbage collectors are used with non-blocking data structures, then what will happen is that the data structure operations will operate in non-blocking fashion, but the data structure will be blocked by garbage collector whenever garbage collection takes place. This defeats the purpose of the data structure being non-blocking. As a result, to truly achieve non-blocking data structures, a concurrent non-blocking memory reclamation system is a necessity. As a result, there have been different approaches towards the solution. Some of them are mentioned here. For example, pointer-based. Objects are not reclaimed if any thread is explicitly tracking it. Reference counting. Objects are not reclaimed until reference count is 0. This has high overheads and cycles may cause an object to never be reclaimed. Garbage collection. Objects are not reclaimed if reachable by any thread. This can take an unbounded amount of time. And quiescent-based. Objects are not reclaimed until all threads become quiescent. epochs. This is the approach we have used, and we may through benchmarks we highlight this is actually quite the efficient one. Next, let's talk about the Partition Global Address Space Model, also acronym as PGAS. I usually tend to call it PGAS, so that's what I'm going to call it throughout the next slide, throughout the whole slide. So PGAS is a parallel programming model that assumes a global memory address space that is logically partitioned, and a portion of it is local to each process, thread, or processing element. The novelty of PGAS is that the portion of shared memory space may have an affinity for a particular process, thereby exploiting locality of reference. Remote direct memory accesses, RDMA for short, are handled entirely by network interface controllers without any CPU intervention. Processing elements cannot access memory on remote PEs via RDMA put get, which are the analog of shared memory load and store operations. Low latency atomics via RDMA is also available on most NICs. As we know, CHIUW is a PGAS programming language. There is a transparent conversion of loads and stores to gets and puts, respectively, with the program it is subjected to when the program is subjected to distributed context. It provides features that enable pseudo first-class distributed objects called privatization. Accesses are redirected to privatized instance of object on each locale. CHIUW also enables writing algorithms in both distributed memory and shared memory in a fashion of write once, run anywhere, with respect to shared memory and distributed systems. What this basically means is that a program has to be written only once, and it can then be executed in both shared memory and distributed systems. Now let's talk about distributed non-blocking algorithms and data structures. With few exceptions, non-blocking algorithms use atomic read, modify, write primitives that the hardware must provide and must be supported by the software. The CHIUW programming language, however, lacks complete support for atomics. While primitive data structure types, data types such as booleans and integers are supported for atomic operations, class objects are not. So to enable non-blocking data structures, our first step was to enable atomic operations on class objects in CHIUW. But this had its own problems. Pointers in CHIUW are represented as 128-bit structs with 64-bit virtual address and 64-bit locality information. However, NICs only support 64-bit atomic operations. Also, they require remote execution atomics, that is active messages, for anything more than 64-bit. And as benchmarks suggest, RDM atomics outperform remote execution atomics by an order of magnitude. So to address these shortcomings, we implemented the module Atomicobject, which supports atomic read, atomic write, atomic compare and swap, and atomic exchange operations on unmanaged class objects. Furthermore, it also provides optional ABA protection to these objects. To achieve this, we compress 48-bit virtual address with 16-bit locality information, which makes 64-bit total for RDMA. However, this does not address the ABA problem, so we extended it to provide solution to ABA problem called the ABA wrapper. This is achieved by attaching a 64-bit sequence number to compress 64-bit pointer. The sequence number is incremented on each successful atomic operation performed of the ABA project. As an example, ABA protected object. As an example, suppose a compare and swap is performed on an object. Then the next compare and swap operations on the same object will fail because even though the address are the same, the sequence number are not the same. Now, since we have a total of 128 bits per pointer, we require 128-bit compare and swap primitives, which is only achievable by a remote execution. It's clear that ABA protection comes with high performance overheads, and it is something that all non-blocking data structures do need. So it has been used internally in our project to implement some more scalable solutions. So coming down to performance, we compared atomic objects to CHIUW's native atomic implementation, that is, CHIUW's native atomic int in shared memory and distributed memory. The atomic int is actually a sibling of the atomic uint, which is the atomic object on which the atomic object is built. Micro benchmarks involving the atomic object test the overhead injected by the abstraction. The experiment evaluates strong scaling, with each task performing the same number of operations comprising 25% read, 25% write, 25% compare and swap, and 25% exchange operations. All experiments were conducted on a 64-node Cray XE50 with 44-core Broadwell CPUs per node, compiled using CHIUW 1.20 with a fast flag to enable all compiler and backend optimizations. The experiments were conducted both in the presence and absence of CHIUW network atomics, which is RDM atomic operations. Shared memory experiments show that all three of atomic int, atomic object with ABA, and atomic object scale linearly with an increasing number of tasks. Atomic object without ABA protection performs equivalently to Chapel's atomic int, and atomic object with ABA takes the highest amount of time, with a constant overhead. In distributed memory, the performance of atomic object without ABA protection is equivalent to Chapel's atomic int. This shows that even in distributed memory, there is no noticeable overhead, and it scales linearly with the number of locales, whether RDMA atomics are used or not. Atomic object with ABA scales linearly with increasing number of locales. It performs equivalently to Chapel's atomic int without network atomics. Future works for atomic objects. Coming this far, it's quite obvious to realize that there are some shortcomings of atomic object, particularly the pointer compression scheme, which limits the maximum number of locales to 2 exponential 16, since locality information is limited to 16 bits. So our future work is to support more than 16 bits worth of locality information. We plan to do this by introducing a distributed table of objects where 64-bit index serves up as pointer to object. As aphorism of David Wheeler goes, all problems in computer science can be solved by another level of indirection. Another shortcoming of the current implementation of atomic object is that currently only unmanaged class objects are supported, as shared type is already wrapped in a record and is larger than 64 bits. Own type is statically managed and cannot be tracked without significant rework to the type, and borrowed types are explicitly tracked by the compiler, making it difficult to track without some significant rework. Another planned future work as a result is to explore possibility of handling managed types, specifically owned and borrowed. Okay, so now let's move on to the primary module of the project, Epoch Manager. As the name suggests, Epoch Manager is built on the notion of Epoch-Based Reclamation and limbo lists. I think we must talk about Epoch-Based Reclamation in brief. So as I mentioned earlier, Epoch-Based Reclamation is a concurrency-safe, lock-free memory reclamation system. It utilizes epochs, which are descriptors for a specific period of time, to determine the quiescence of objects and determine whether they are safe to be reclaimed. Concurrent-safe memory reclamation is a non-trivial problem and is at the very root of non-blocking algorithms and data structures. Our goal was to adapt this memory reclamation technique in the distributed memory. The diagram is an illustration of epoch-based reclamation adapted to distributed memory. Given two locales with two threads each, the illustration begins in epoch 0. At time t1, the global epoch is 0, but locale 0, thread 0 is still in epoch 2, preventing an advancement to epoch 1. At time t2, the global epoch is safely advanced to epoch 1, and after locale 0, thread 0 becomes quiescent, even though locale 1, thread 0 and locale 0, thread 1 are in epoch 0. It is safe to advance the epoch as epoch 0 is only one epoch behind. Locale 0, thread 1 remains in epoch 0 from t1 through t3, preventing the epoch from advancing until t4, where the global epoch is then advanced to epoch 2. At t5 and onward, the algorithm continues much the same. With further explanation, I think this would become more clear. So, moving on to limbo lists. In the design reclamation system, objects that are marked for deletion during an epoch are deferred for reclamation. They are held in limbo lists until they are safe to be deleted. We designed a data structure called limbo list to handle this operation. There are two phases of limbo list: concurrent insertion and bulk deletion. Limbo lists have been implemented using push exchange stack. Both the insertion and deletion operations are wait-free. Here is the code snippet of the push, that is insert operation, and pop, that is delete operation. As you can see, we only make use of the atomic exchange operation. This allows the list to function correctly without requiring any compare and swap operation or ABA protection, making the list highly efficient. Epoch Manager is privatized, in that an instance of the Epoch Manager is created and maintained on each locale, and all accesses to the Epoch Manager are forwarded, such as the case for field accesses or method invocations, to the instance that is local to the locale. Each locale maintains 3 epochs corresponding to the current epoch E, previous epoch E-1, and the epoch before that E-2, which can alternately be stated as E+1. All operations are modulo 3. Each locale has a local epoch, while there is one global epoch for the entire reclamation system. This is the illustration of Epoch Manager when global and local epoch is 2. Each locale manages its own privatized instance where all accesses are directed to. Limbo list 0, shaded gray, is free to be reclaimed and there is a guarantee that no active task will be in epoch E-2. Limbo list 1 is yet to be reclaimed and limbo list 2 becomes the current that all new reclaimed objects will be added to. Local epoch acts as locale private cache for the current epoch, reducing necessary communication. An atomic flag must also be acquired to advance the epoch, first locally and then globally, wherein failing to do so will cause the attempting thread to back out, non-blocking. Tokens. Tokens play a key role in Epoch Manager's functioning. A token is basically an object that is issued to each participating task. Tokens act as the task handle to Epoch Manager. It keeps track of the registered task status, that is whether it is active or inactive. Active simply implies that a task is in a critical section and is accessing a shared object. In case of an active task, its token keeps track of the epoch in which the task is engaged in. For the reclamation scheme to work, each task must register to the Epoch Manager by calling the function register. To free a token, a task must unregister. Unregister is automatically triggered when a task goes out of scope, so it is completely optional. Tokens aren't actually deleted. Instead, they are recycled. Tool lists implemented as lock-free queues are used to manage tokens. Allocated list, which is the list of all allocated tokens so far, and free list of free tokens ready to be recycled. When a task unregisters, its token is added to the free list. So in case free list is empty, a new token is allocated. To enter critical section, that is to access shared objects, a task must pin its token. Pinning marks the status of the task as active. A task is always pinned to the current locale epoch. While a task is pinned, its local epoch cannot be updated. Objects deleted go into the corresponding epoch's limbo list. This is all pretty straightforward here. To exit a critical section, the task must unpin. Unpinning marks the task as inactive. Here's an example usage of the Epoch Manager. As we can see in line 1, a new instance of Epoch Manager is declared. Line 3 depicts registration of a task and acquiring of a token. Line 4 depicts pinning of a task, while line 5 shows how a task unpins. Line 6 depicts how a task registers. Next, we have an example depicting the usage of Epoch Manager in for all loops. Notice that we register to the manager using the with statement and not inside the loop. This allows for registration on per task basis instead of registering each time the loop executes. As tasks go out of scope, they automatically unregister. Line 11 depicts how an object is deleted, that is marked for deletion. Line 14 depicts the function called to clear everything that has been marked for deletion. Note that this is a forced delete and might not be concurrency safe. The concurrency safe method is called try reclaim, which we shall discuss next. So global epoch can be advanced by calling try reclaim on the task token. This in fact is the only way to advance the global epoch. In epoch-based reclamation scheme, reclamation is performed only when the global epoch advances successfully. Global epoch can advance only if no active task is in an epoch previous to the global epoch. A task is in the same epoch as global epoch does not affect global epoch advancement. On successful advancement, Epoch Manager reclaims objects which are safe to be reclaimed, that is, the object marked for deletion in 2 epochs behind the new global epoch. Since remote objects may be marked for deletion, each locale first constructs a scatter list of remote objects to be deleted that sorts objects by the locale they are allocated on, significantly cutting down unnecessary communication. After this process, the marked objects are reclaimed. So in a nutshell, this is all there it is about Epoch Manager. Epoch Manager has been developed with the intention of using it in distributed memory, but thanks to PGAS, Epoch Manager works in shared memory as well. However, we developed a much more optimized version of Epoch Manager for shared memory intent called Local Epoch Manager. The internal functioning and components are identical to Epoch Manager except for the fact that there are no more local epochs. Local Epoch Manager does not take remote objects into consideration either, so it does not create any scatter list of remote objects before reclamation. Moving on to the performance of Epoch Manager, again, as I mentioned earlier, all experiments were conducted on a 64-node Cray XE50 with 44-core Broadwell CPUs per node compiled using Chapel 1.20 with a fast flag. The experiments were conducted both in the presence and absence of chapel network atomics, which is the RDMA atomic operations. We evaluate the scalability of Epoch-Manager under various workloads, which should be representative of the different use cases. In a read-only workload, such as for a read, often, write, rarely data structure, such as when performing a lookup in a hash table or linked list, it may be suitable to just pin at the beginning of the operation and then unpin at the end. Demonstrated in the figure, performance is essentially stable across multiple locales, demonstrating that even in distributed context, it can scale reasonably well as all locales forward their access to their privatized instance despite being in a parallel and distributed for all loop. Next, another typical workload is analyzed where no reclamation is performed until the very end, which is typical when the number of objects is bound and can fit within the memory without running out of memory. The number of remote objects to be reclaimed varies by 0%, 50%, and 100%, which measures the overhead of reclaiming remote objects. As the result suggests, Epoch-Manager is embarrassingly parallel in this scenario. It scales in distributed memory, and this highlights privatization benefit, especially of locale private limbo lists. The Epoch-Manager scales even in the case where try-reclaim is invoked with increased frequency, as demonstrated by the results displayed in the figure. When reclamation is performed, not even the locale where the global epoch is allocated is bogged down by redundant requests thanks to the first-come first-served election of tasks, and scales equally both with and without RDM atomics. This highlights the benefit of scatter lists for reclamation. In the case where the user does not want to take any chances and attempts to try reclaim on every iteration, there is skill scalability, as shown in the figure. This further highlights the benefit of scatter lists for reclamation. Future work. The planned future work for Epoch-Manager is actually to develop distributed data structures which make use of Epoch-Manager to depict its efficiency. One such data structure is under development by us called distributed interlocked hash map. Some benchmarks that we have collected are on the screen. In a typical workload of 80% find, 10% insert, and 10% delete, the shared memory version of the map outperforms the chapel standard maps by 60 times. The distributed map on 64 locales benchmarked up to 1.5 billion operations per second, one operation being an insert, find, and delete operation. And this is being achieved while also maintaining concurrent-safe memory reclamation. Clearly, the performance is in orders of magnitudes faster. More data structures are planned and are yet to come. So wrapping things up, the Atomicobject is a solution to the problem of lack of language support atomic operations on objects. The implementation not only provides the operations in shared memory but distributed memory as well, utilizing pointer compression that enable RDMA atomic operations, which are on par with the performance for atomic operations on integers, while also providing protection from the ABA problem with memory reclamation by usage of double word compare and swap. The Epoch Manager, a non-blocking epoch-based reclamation garbage collection system that allows for concurrent-safe reclamation even in distributed memory context. Both of these are essential building blocks for developing non-blocking algorithms in both shared memory and distributed memory. Thank you. Feel free to contact me or Louis at the given email.